In this video, we're going to learn about logarithmic functions, and those are going to be defined as the inverses of exponential functions. So let's kind of see how that comes about. We saw in a previous video about trying to find an inverse function of something. You replace the fx with y, you switch your x and your y, and then you solve for y here. So if I wanted to find the inverse of the function 2 to the x, that was the exponential function we saw in a previous video. We set y equals, switch our x and our y, and then we want to solve for y. Problem is, how? Right? Again, you have x equals 2 to the y. How in the world are you going to get y by itself? Well, it turns out people studied this problem, and they discovered that there are no algebra steps that you can use that will let you get the y by itself. You can't add both sides, you can't subtract both sides, you can't multiply both sides, you can't divide both sides, you can't square root, you cannot cube root, you cannot square, none of those things are going to get y by itself. So what they did was they had to create a new symbol to reverse this process. For some reason, I don't know who decided this, but they decided it wasn't going to be just a single symbol like, square root or something. They were actually going to write a little word here. And so the solving of y here, the new symbol they use is the log symbol. So you write log, and then you put the base, which was 2 there, and then you put what it was equal to, x, and then this right here, it means what y would be solved for when you have x equal to 2 to the y. And again, this was a new symbol created just to solve this problem. And then it was also discovered later on that this will end up being very useful by itself, let us solve other problems. But for right now, at least, it was just created to have an inverse for this exponential function. And if I want to make it more generic, instead of saying the base is 2, if your base is any number b, then x equals b to the y means the same thing as y equals log base bx. And I want to say this is one of the single most important things in all the logarithm stuff that we're going to do in this class. If you get this down, that will probably solve, I don't know, somewhere between 30 and 50% of the problems by itself. It is that important. Basically, you want to be able to convert back and forth between exponents and logs. So when you have something like x equals b to the y, you always write down log. Use whatever base you have in the problem. Then whatever the exponent part is equal to, that's what goes next to the log. And then the whole thing is equal to the exponent. So what you want to think about it is logs are what exponent you have. That's what the log is. And on the other hand, if you start with something that has a log in it and you want to go backwards, it's actually a little bit easier this way. You start with a base, you raise it to the right side power, and it equals what's inside. So b raised to the y equals x. And again, you really want to get this down, switching things around. Okay, so how do we graph these things? Well, I'm going to start by making ourselves a little table here. The only problem is, since we can't very easily plug in numbers into this log function because it's a new made-up symbol, what I'm going to do here is realize that when we're doing inverses, right, this is the inverse of 2 to the x, then inverses, they switch your x and your y here. So before I had -2, -1, 0, 1, 2, and then we had these values here. And so what's going to happen then is when you take the inverse here, you're switching it around. So instead of x being -2, y being 1/4, x is going to be 1/4, y is -2. And so I'm just going to switch all of the x's and y's here. That's what inverses do. And then when I go to try to plug these things in here, it's going to look like follows here. And it turns out this is what your logarithmic graph is going to look like. Okay, so, and you can kind of remember that when you have inverse functions, they're supposed to be mirror images along the line y equal to x. So you can kind of see the mirror image there of this log graph. This is 2 to the x, roughly. This is our log base 2x, roughly. So you can just think in general it's going to be like that. So down here when I have log 5x minus 1, it's going to look like that, but shifted right 1. So something like this here. And then the only thing here is that when we have log base 4x, right, we have log base 4x, that base number is smaller than 1 here. So it's not going to be the exact same type of graph. It's going to be flipped a little bit here. So why don't I just try to do that with our inverse idea here. So we know what 0.4 of the x looks like. It's coming downwards. So we're going to still have, flipping around, we have something like this here. And then, let's see here. Something like that. Okay, so what can we say about these things here? There's no horizontal asymptote this time, but they do have a vertical asymptote. The default's going to be at x equal to 0 here. Of course, if you have things shifted over, I was not careful enough over here, because this is a graph that shifted right 1. It's now going to have a vertical asymptote at x equal to 1 here. There's going to be no horizontal asymptote. It is going to go off to infinity or negative infinity, depending on your base. There will be no y-intercept. There will be an x-intercept. The default is going to be at 1, 0 here. Again, if you shift it, it will change. There's also an important thing on these ones. The domain of an exponential function is all real numbers, but the domain of these logarithms, they only exist to the right of 0, so it changes your domain here. And that's going to be one of the things we're going to see in other sections, is that the domain of logs, you have to make sure that everything is positive as a result. Now, it doesn't necessarily mean that x is positive. It means that whatever's inside the log is positive. So for this one down here, we would take whatever's inside here, x minus 1, and we want to make sure that that result is positive. So in this case, the domain would be 1 to infinity. Okay. Now one last thing before I close out this video. We've created this new symbol log, and we always have a base for it to tell what's going on. However, sometimes we will write just log with no base number. And in fact, that's the log button that's on your calculator. And the thing is, that means log base 10. So, how we use base 10 as our numbering system, log base 10 is a fairly standard used logarithm. And so they decided to shorten it, make your life easier by just not writing any base. So you will never see log base 10 in your book. It'll only just say log, and it means log base 10. I know that can be confusing, but that's just how it is. And the other one that's a little bit special here is that it turns out using the number e as a base ends up becoming very important in a lot of applications. And they didn't want to write down log base e over and over again, so they shortened it, and they just call it lnx. That stands for natural logarithm. And so lnx just means log base ex, and you also should have a button in your calculator for ln. So your calculator can default do ln, can do log base 10, and then you may or may not have another log button on there that allows you to do log with any other base. You'll probably need to explore your calculator to see if it has it or not.